All right, here's page 2 of our semester 2 review. We want to write a number with 2 leading zeros, 1 trap zero, and 4 overall significant figures. So for leading zero, we need decimals. So here are our 2 leading zeros here. Then we need a number. This number could be any number. Let's choose the number 5. Okay. Then we need a trap zero. Trap zero is going to be a zero between 2 non-zero numbers. So I'm going to put that. So here is our trap zero. Let's put that in a different color arrow. That's our trap zero. And right now there's 1, 2, 3 significant figures, so we need to add one more digit. This could be any number. And I could put a 0 here. That would count. Any value, any number that we put in here would work. A 0 would work, or a non-zero number. They're all going to count. The 0 counts in this case because we have a decimal, and this would be a trailing 0. All right? But lots of different acceptable answers would be that you could have for this one. All right? For number 8, we want to draw a ruler to use to record a measurement of 3.5 centimeters. So this is our estimated digit, or our guess. And so that means that it must be calibrated in the ones place. And so what that means is that when we draw our ruler, the smallest value that we have would be to the 1 centimeter. So if I was measuring a line that was 3, and I was measuring it as 3.5 centimeters, it would be something like this. And we would be estimating that our line that we drew would be halfway between the 3 and the 4. All right. In contrast, for number 9, we want to draw a graduated cylinder that would record a measurement of 10.55 milliliters. So our estimated digit happens to be the second 5 here. So what that would look like is we would have a 10, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, and then this would be 11. And then so kind of zooming in, the level of our liquid would be, the bottom of it would be somewhere halfway between the 10.5 and the 10.6. So measuring from the bottom of our meniscus. All right. So I would say that this is calibrated to the tenths place. And so that means that each of those lines that we see here is worth a tenth. All right. Getting into mixing hot and cold water, the epic days that when we did that in class. All right. We want to draw 2 graphs. One that would represent our data from mixing more hot water and mixing more cold water. So let's start out with the more cold. So if we have more cold water, what that should tell us is that the final temperature of our mixture should be closer to the initial temperature of the cold. All right, so we have our Ti of our hot over here. We would have our Ti of the cold here, our initial temperatures. And then our final temperature would be closer to the initial temperature of the cold. All right. If we had more hot water, it would be sort of the similar graph, just flipped. And so our final temperature would be closer to the initial temperature of the hot when they mix. All right. So again, Ti of the cold, and then you would have Ti of the hot. And then we'd have our final temperature again being closer to the initial temperature of the hot. All right. For number 11 here, we were going to draw a phase change diagram, temperature versus heat. So temperature would be on the y-axis, heat would be on the x-axis. Heat is increasing as we go to the right. So we're going to draw our phase change diagram, labeling our states of matter. So I'd have solid, solid plus liquid, liquid, liquid plus gas, and gas. In terms of our phase changes, I would put down here melting in the solid to liquid when you have both of those. And then I would have maybe boiling up here. Okay, again, this is as we're heating our substance, moving from left to right. Changes in kinetic energy. We want to remember that temperature is our measure of our kinetic energy. And so wherever temperature is changing, that's when you're going to have a change in the kinetic energy. All right? So that would be in the solid area, the liquid, and the gas. If we were talking about the energy of position, which is your potential energy, then you're going to have changes in your potential energy in the melting and the boiling. So all the heat in these flat areas is not going to changing the temperature, it's going to change the position of the molecules. Kind of remembering that solid particles are very rigidly organized. Liquids are sort of more loosely arranged, still in contact. So in this melting stage, you have sort of a combination of this rigidly packed formation turning into something more loosely arranged like this. That's what's happening here as we're adding heat. In the boiling stage, what we have is that, think about gases. Gas particles are they're not in contact with each other. So when you reach the boiling point of your liquid, all that energy that we're adding as we go from left to right, all that energy is going to turn it from something that's connected to separating them, again, changing their position. That's why your potential energy is changing. All right? What would things look like if we had a cooling curve, like a number 12? Then if we had a cooling curve, basically it's going to look like the reverse. So we'd be starting with a gas. As when you reach that point of condensation, which is the same as the boiling point, that gas would then start condensing into a liquid. Okay. When all that gas is turned into a liquid, then it's going to be purely in the liquid phase. Then we cool it down further. That liquid then starts turning into a solid until it becomes completely a solid. So this would be what our graph would look like for a cooling